today's today's talk it has a bit of overarching topics within forensic age estimation. I will talk a bit more on age data estimation, and Venema will talk a bit more on legal age estimation, especially on computer vision and deep learning techniques to address problems in legal age estimation. And what we hope that despite all these things that are going on, by the end of this talk, you can see that everything is like the Panacea's logo. Despite everything is branching, everything is deeply interconnected. And in fact, I think that for advancing age estimation, we need to really think of age estimation as an interdisciplinary effort, although it's for the purpose of age data estimation, of legal age estimation. Usually you think of age estimation as something deeply rooted in the biological and the medical sciences, but computer science, artificial intelligence, machine learning plays a pivotal role here, especially for advancing research and practice in this field. It's not merely a publication trend, is not merely the buzzword of AI. No, I believe that it's critical because, I believe you will see, we will do our effort to show you that artificial intelligence, machine learning is key to not only exploit a given biomarker, let's say skeletal markers, but also to integrate information from the different biomarkers, and of course provide not only the most accurate age estimates, but account for uncertainty, because in forensic sciences, modeling uncertainty is very important, and nowadays even more. This topic, forensic age estimation, is at this moment a very fertile field of research, and I believe it will remain for the future to come, because there are these very important and significant challenges we need to tackle, and especially for the relevance of today's talk. Improving multifactorial and multimodal approaches, of course, is key to overcome challenges in age estimation. But here, bringing the best of computer science to this topic, for instance, using computer vision, as Venema will show, to address the issues related to observation error, observation subjectivity, is also key, because as you all, especially those who are practitioners in forensic science, you know that we rely mostly on morphological scales, and to assess be it in forensic, be it in age data estimation or legal age estimation, we rely a lot on these morphological scales and staging, and we all know that is sometimes deeply subjective to assess based on these scales. And here, bringing the computer science into the game is pivotal to, for instance, account for this issue. And of course, in age estimation, we know by the biological theories that underpin it, we know that age is not a linear process. Be it even if we account for subadult aging, things are not as linear as we like, and that of course is a call to use more flexible and robust estimation methods, and of course multifactorial and multimodal approaches, so that we can account for the biological variation that exists in aging. and in this way produce more accurate age estimates. In specific, now I will be a bit more specific and focus a bit more on adult aged death estimation, because it's a topic that I know very well. I devoted last years exploring this, and here we know in the context of age estimation that the practices especially to how to report, how to combine information are often vary a lot between practitioners, and something that always comes up is the need and how to use to combine the different indicators you can assess in a skeleton in a way that you can have a more accurate age estimate. So here we are pushing forward to a multifactorial approach, playing here the role of both an advocate and the devil advocate for a multifactorial approach, because it's not always straightforward. A straightforward choice, although the literature points that using a larger array of information produces better estimates. It's not always translated into practice, but the pros in that regard of using an approach that takes into account a larger array of skeletal traits, for instance, is that we produce more precise age estimates, specifically for older individuals. But of course, this is not only magic, and it also comes with some caveats. For instance, lack of standardization. There's a lack in the literature of best practices for combining indicators and methods that are easy to use when you are using multiple indicators. It also comes with increased methodological complexity, both to model age estimation as a mathematical problem, but also from a practical perspective, you need to be proficient in scoring a larger array of skeletal features, for instance, and you can have a problem of propagation of errors if you are combining existent methods. You can be propagating the limitations of each of those methods into your final estimate. And this, of course, comes to this decision that as practitioners, as anthropologists, have to answer to, is how exactly do you combine, what is the best method, which should you choose. And here you, of course, this can be something more specific to certain judicial contexts. But for instance, in the US, you would have like this adversarial system where there's a chance that your report be completely contested in court, and someone asks you, okay, but you had the entire skeleton. Why did you base your estimate only on the pubic symphysis, for instance? That kind of questions may arise, and so having multifactorial approaches is in fact important. So within the literature, you can think of the existent things as I grouped it this way of you have procedures for multifactorial age estimation. You have like methods that are developed from scratch to account for multiple traits. Within these procedures, you have things, for instance, this first paper from Lovejoy, it's really old, it's from 1985. And for instance, it uses PCA as a way to combine. You have some things that are more sophisticated mathematically, I would say even very complicated, not sophisticated, but complicated, such as using fuzzy logic as proposed by Anderson. You have also other approaches such as the two-step procedure that is like a domain knowledge heuristic where, for instance, you would use if your pubic symphysis is below stage 3, you will remain with that age estimate. You know that the method is accurate for that age range, someone below the 40s, for instance. And if your pubic symphysis is a higher stage, you would forget the pubic symphysis, and then you would make the age estimate based on Lamendin technique, a dental technique. And this is a sort of a domain knowledge, how to integrate domain knowledge and how to use anthropological knowledge to produce basic heuristics that are not complex but effective. On the other side, you have, for instance, methods like this one proposed by Roger Imailer to combine the acetabulum and the auricular surface. Comes with a problem that if you cannot score one of the features in one of the indicators, you cannot use the method because it relies on a sum score of, I believe, 7 different components. And if it's one it's missing, you cannot use the method, although it's very accurate for older individuals. And you have other approaches such as transitional analysis, and that I believe that we will hear more about it in the future. As I think there's a lot of especially conference procedures that you can see from this research team. It's a method that uses probabilistic estimators to combine multiple indicators, much akin to this last paper by me, where I will talk a bit more of this particular method that I developed for multifactorial age estimation using deep random neural networks. So I will guide you on a very quick overview of this work I developed. So I developed a macroscopic protocol that accounts for up to 64 skeletal traits from various regions of the skeleton, and uses very simple scoring schemes. Either it's binary or a ternary, 3 stages at maximum to describe a specific feature. And to do so, I collected a data set which is publicly available for anyone who wants to use it and improve on this topic, from identified skeletal skeletons from 2 collections in Coimbra, where I developed my studies. And the way that all these indicators are combined in a final estimate is through a deep neural network, a deep random neural network specifically, that is just like a normal neural network for those who are familiar with it. For those who are not familiar with it, essentially in a neural network, very quickly you have your input, and then it is combined through these intermediate layers, where you have each of these H is essentially what is called an artificial neuron, but essentially it does in a first stage a linear combination of your traits, and then applies a nonlinear function, an activation function. And when you aggregate all these functions together in a final layer, you have essentially a neural network that is a very powerful functional approximator, and it was a successful approach here. Just the key feature of this type of neural networks that I use is that the weights are randomly attributed at the first, and you only train the last layer of the net that is equivalent to do a linear regression on a bunch of features, and that are your original features, as well as a large composition of your features and combinations of the intermediate features and so on. And the whole thing trains with very simple mathematics, unlike most of the more advanced neural networks. And that's it on that side. Something that I tried to focus was also on uncertainty modeling with two different approaches, but related, using variance models. So in addition to the neural network, we train another model to predict the error associated with a specific prediction. And in this way, we can construct predictive intervals to account for the uncertainty in the estimates. We can explain or give more details on this in the questions if you have them. So some results based on computational analysis, where in a first set of experiments, we divided the traits we have in blocks similar to the traditional methods, like a block for pubic symphysis, one for auricular surface, and so on, and also tested against a model using all the features at the same time. And we also did another block of experiments where we simulated a random percentage of missing traits to account for more realistic scenarios. Usually in forensic cases, you don't have perfect, pristine, and complete skeletons, and this also to give some insights on the usage on the accuracy of the method when you don't have all the features. And very quickly, the key points. The best performing model was, of course, the full model with the 64 traits. You can see here in this scatter plot that it predicts age with a R-square of 90%, almost 90%, 89 to be precise. But it can predict also very well the age in advanced for older individuals, which in itself is an advancement in the state of art of skeletal age estimation. Here you can see the efficiency. The predictive intervals are in fact well calibrated, and you can see that they, even for older individual people below above 70 years old, the method provides specific age estimates. And if you use only, for instance, the traditional methods, you will have a similar result, but not so specific for the elderly. And for instance, if you use only the generative traits, you can obtain, by that I mean only vertebral degeneration, joint degeneration, musculoskeletal degeneration. You can obtain very accurate estimates as well. But of course, if you only use those traits, the estimates for younger individuals will look not, I wouldn't say terrible, but inspecific for younger people, because there's nothing there to signaling that it is in fact a younger individual. From the experiment B, when the random traits, based on random traits, the key point of this experiment is that we were able to demonstrate that as long as you are combining different traits, you are injecting different traits in your model, you can obtain good estimates, models that are very performant, in line with the accuracy of a full set model. And in itself, it's especially for practical applications, it's insightful result from this experiment. Based on this research, I developed this little piece of software called Drainage that implements the old protocol from data scoring to age estimate. Here I will just emphasize the three main screens. So estimate, it outputs an estimate with uncertainty that is critical. It has some embedded explainability to here using a linear surrogate model to predict the estimates by the neural network. But I think we can explore that in the future, in the end, if there's some questions. But I accounted for explainability, and it also, for any model you predict, it will compute some metrics to give you an idea how the model fares. Some validation studies already conducted on this approach. We have this study by Galemani. It's in a conference procedure. Here was in a Chilean sample tested both the RNH network algorithm against multivariate cumulative probit, which is a Bayesian algorithm for age estimation. But the key point from all these three studies, Galimani, Roos, and Cornelio, is that the accuracy was within the line of what you have seen, and favoring good results. Of course, room for improvement, but although I see it as a functional prototype, at least in different populations. So this is a Chilean population, Cruz is a Dutch sample, and Cornelio is a test on a Brazilian sample. It works fairly well. But there's also this study by Rizos, who tested the RNH in a Greek sample, and for instance, for very old individuals, the method fares very well. But here I highlighted this because it's really important. Despite I developed the macroscopic protocol is quite simple, binary or ternary features. Were not as reproducible or repeatable as I would like it to be, and somehow it is expected. We know that it's more or less impossible for two human experts reproduce entirely these staging schemes associated usually in the age estimation. And of course, this study reinforces the importance of cross-validation, but also, for me, reinforces that there's the idea that there's so much we still need to do to improve age estimation. And one of the things we need to improve is, in fact, how to move from human-based scoring to something more repeatable, and for instance, using AI to look at the bones. And with that, I will leave now for my colleague Venema to speak about legal age estimation and focusing on computer vision approaches to the topic.
Now that David introduced the concept of age estimation and explaining a little bit, I'm going to focus on, well, as he said, I'm going to focus on legal age estimation. And in fact, I'm going to explain the developments that we did within the project UMAFI. This is a European project for legal age estimation of unaccompanied minors using artificial intelligence. It has been like 2 years working on this. But first of all, I want to give a brief motivation on why it is important to estimate legal age of minors. I'm sure that you are familiar with this, but it is always good to have like a reminder of it. So we have different situations where this is important. For example, more than 13,000 minors applying for asylum in the European Union in 2020, and they are undocumented, so you need to estimate the legal age. Or 12 million girls that are married and are under 18, for example. So regarding how this is done, we base our developments on the European protocols that have been established here in the European Union. And they are based on the analysis of an X-ray of the hand, where you can see the development of the carpal bones, an X-ray or an orthopantomography of the teeth, where you can see the development of the third molar, and lastly, a CT scan of the clavicle, where you can see the development of the clavicular epiphysis. So this is how legal age is supposed to be estimated, or how it is estimated nowadays. But what is currently used in forensic practice, like the methods that they use, have different problems. And I highlight here 3 of them. They are difficult to apply and to replicate. They are subjective because they depend on the expert that performs the evaluation, and they can be inaccurate in many cases. So as an alternative, the AI-based methods can provide methods that are objective because they don't depend on a human observation, and have a high discriminatory capacity because they are trained in a lot of samples. And if they are trained with the correct data set, they can be robust and replicable. And I'm going to talk more about that, because the methods that were in the state of the art before these developments were not robust because of the data sets that they used to train them. So what we propose is to fix the main problems that we think that there are in the state of the art for legal age estimation using AI, and these are 3 main problems. They don't follow the established protocol, so they don't use the hand X-ray and the teeth X-ray and the clavicle CT. They lack robustness because they have been trained with data sets that come only from one place. So if you want to apply the method to individuals from other places, they don't work. And they also have a lack of acceptance because, in fact, they are not used by the forensic experts. They keep using the traditional approaches. And then also, depending on the approach, like on the AI approach that you use, you can use deep learning on the one hand, but you have a problem with explainability, although the methods are very accurate. And then you can use machine learning using macroscopic observations, which are more explainable, but they lack accuracy. And they are also subjective because they depend on the expert annotations. So as I said, what we propose is to develop our methods based on artificial intelligence, like fulfilling the established protocol. So we want to develop at least 3 methods, one for teeth X-rays, one for hand X-rays, and one for clavicle CTs. Then we want to use data from multiple populations of all continents so that the method is robust to different populations. We want to develop a model that is holistic so that it is more explainable by fusing all the available information. And then we want to validate the developed algorithms in real cases of undocumented minors so that the acceptance is higher. So I'm going to explain these 3 methods that we develop, and then David will go through some explanations on how we plan to fuse them all in just one method for legal age estimation. But first, I will just talk a little bit about how they work in general. So starting with the method that estimates legal age using the teeth. This is our data set. This is the biggest data set that we have. So it is like the most robust method that we have developed. We have data from 12 countries and 4 continents to train, validate, and evaluate our method. And then we also added examples from 4 different countries that were not contained in the initial data set. So it is like an external validation, like a simulation of real forensic scenarios, because it is data that come from places that we have not trained with. So probably one of the most boring tasks, but also one of the key tasks that we have performed during this development is the unification of all samples into one. That is because of 2 reasons. First, if the neural network sees images that look approximately the same, it will be easier for it to find the relevant information in the images. It will not focus on, for example, these letters that appear in an image or this black stripe that appears here. And also because if we have different samples with different age distributions coming into our model, if the model is able to estimate which sample does an image come from, it will be able to bias itself towards an age estimate. So we don't want that to happen. So that is like the key part of the project. It is not the most interesting thing scientifically talking, but it is probably the most important thing that we did. And then once you have pre-processed data set that looks appropriate to train a neural network, it is, let's say, easy to do it. So we just have an X-ray a teeth X-ray that goes through our neural network. So this neural network has like two parts. So in one part, it receives the image and it learns like a representation of the image. So it applies some mathematical functions and learns like this representation, and then uses that representation also using some mathematical functions to estimate like the most probable age for that specific input to the network. So what we do is to estimate that most probable age. So that is what the methods that had been developed before did. But we also added first the integrated gradients algorithm to obtain an activation map that shows where the network is looking at. And then we also used conformal prediction that David already mentioned before to compute a prediction interval around the most probable age. So we want to use this to have like an uncertainty measure on what is the age span where an individual should fall. And this is like a real output of the model that we have. So it provides like the most probable age, then a minimum age according to a prediction interval of a certain coverage, and then it gives some statistics so that the human expert that is using the method can decide whether the individual is a minor or an adult. Regarding the results, in our test set, we got a mean absolute error of 1.12 years. And in the different data sets that we used for this external validation for this real forensic scenario simulation, let's say, we get an error between 1.20 and 1.50 years that when compared to the state of the art, which was 2.20 years in the same data sets, is very good. And then we have these plots that show the distribution of the errors around the whole age span from 14 to 26 years old, where you can see that the model works pretty well from 14 to 23, and then it starts worsening a little bit from 23 and on. Also regarding results, I want to show the output of the prediction intervals that I mentioned earlier. So the idea is that when you have the original model, if you use the most probable age that the model estimates, you misclassify 150 minors as an adult. However, if you apply the minimum of a prediction interval of a 90% coverage, you only overestimate the age of 15 minors. And that comes with a decrease in the general accuracy of the method, but it is like there is a trade-off between how ethical the method is and how accurate the method is, and that is where the human expert comes in. So as I said, this will allow us to apply the minimum age concept when combining this method with others, so that we can say that someone is a minor, like with the highest standards of proof. And then this is, as I said, that what you can see in the green line is that the predictive positive value. So when you estimate an adult, the individual is in fact an adult, increases if you increase the coverage level, but the accuracy decreases. So there's this trade-off. And also regarding results, we wanted to see why did the model had some high error. So for example, if you look at the first row, this is a real estimation that the model does. It is 15.31 years. And these are the estimations of a human expert, 16 years, but the real age is 24 years old. So we see that the artificial intelligence misses by a great margin, but also does a human expert. So we guess this is a problem with the labeling of the individuals, or probably with the development. So it is not intrinsic to the model. And as I said, also, we get these activation maps that show where the model looks at in order to estimate age. So as you can see, it looks mainly at the third molars, at both the upper and the lower ones, but it also looks sometimes at the second molars. So it is, I mean, it looks where human experts look, so it makes sense to think that it works correctly. And we combine all of this in a tool that is already deployed in our website, and you can access it. It is online and it is free. And you can use it to estimate legal age using this method and teeth X-ray. And in fact, we used this website to perform a validation study with 24 international experts that estimated the age of 20 real cases. And here I show the results. So you can see here that for a human expert that is not using AI, the mean error is of 1 to 20 years. And the 95 percentile, I did not take the maximum because I don't want outliers to come into the distribution. So the 95 percentile of the error is 3.43 years. However, if they use AI, the mean error reduces to 1.10 and the 95 percentile reduces to 3 years old. And when AI is used alone, the mean error is reduced to 0.99 and the 95 percentile is 2.59 years. So this shows that at least AI improves the results of the expert, and there is a competition between expert plus AI and AI because these results are usually more ethical than these ones. It always needs like a supervision to make the decision of what age to really estimate. So that is like the most, like the biggest method that we have developed. So these explanations now will be a little shorter. So I'm gonna go now with the legal age estimation method using the hand X-rays, and I follow like the same structure. So first the data set, in this case, it is not that big. It only contains 6 samples. The advantage is that 2 of them are public. But as you can see, we have like a problem with the age distributions. Like most of our individuals are below 19. We hardly have any over that age. But we don't really worry about that because in the end, our purpose is to develop this multifactorial method. So probably the hand is going to be more accurate here before the 19 years old. And here we will use combination with the teeth and the clavicle. So we don't worry a lot about it. Again, the most important part for the development of the method is data preprocessing. But in this case, it is much easier. You can just use a technique that is called histogram equalization that just distributes the gray levels of the image around the whole span from 0 to 255. That is the range where you can store pixels in an image. As you can see, it goes from here to here, so you can see that these images look much more similar. Once you have this data preprocessing, the method is just the same thing as with the teeth X-rays. So it is a neural network that provides the most probable age. Then you have the explanations with these activation maps, and then you have these prediction intervals to compute the minimum. So I'm not gonna stop in that again. And I'm gonna go directly to the results. So in this case, in validation, we have an absolute error of 0.63 years. So the method is very precise. And we only miss 8 minors as adults, and all of them are over 17. However, we get a lot of errors from adults. We estimate 21 adults as minors. So again, as a distribution, as I showed before, the method works very well from 14 to 19 years old, and from 19 to 20 or 18 to 20 gets a little worse, and it is terrible from 21 and on. As I told you before, we don't really worry about this because the age span where it works is probably the one that we want to use in our multifactorial method. And lastly, we have this method for legal age estimation using CT scans of the clavicle. Again, I'm going to use like the same structure. So again, the data set, one more time, from 14 to 26 years old. In this case, we have 1,189 full body CT scans from the New Mexico Descendant Image Database, which is open and public. And as you can see, we just have a few samples below 17. So, I mean, that could be a concern, but it happens like with the hand, but the opposite thing. Right now, for the clavicle, we know that it is going to be precise for all their ages. So it is not a big deal for us because here, we just have the hand and the teeth. So it is of no worries to this multifactorial approach. And then we have more men than women, but we evaluated the results on that, and it doesn't seem to be a problem. So regarding the method, this one is more complicated and it probably requires like a lot of technical knowledge. So I'm going to try to make it very simple. We have like 3 steps. We have a step for clavicle detection. So this step in green, the image receives a full body CT, then segments the skeleton in it and gets a vector that describes every bone in the skeleton. Those vectors are fed into a machine learning algorithm that is able to tell which one of those are the left and the right clavicle. Then this left and right clavicle go into the second step, which is for the selection of the most important slices of the CT in order to estimate age. So what we do is that we take 5 equally spaced slices from the coronal or from the axial view that show the medial epiphysis and feed them into an age estimator. But then we don't use that to estimate age, but to use the integrated gradients algorithm that gives like an importance score to every one of these equally spaced slices. And using those importance scores, we can get which one of these slices in the clavicle is the most relevant to estimate age. Then we can take that slice and some slices that are close to it in the CT space to estimate the legal age. So we use those 4 images, 2 from the coronal view, 2 from the axial view, to estimate the age from the right clavicle and from the left clavicle, and then take the mean as the estimation. And of course, we also use this prediction interval thing to estimate the legal age as an interval. So that is the method. Regarding the results, our method gets an error of 1.36 years in validation, which is much better than the state of the art in the same data set, which is what I show here, from 2.40 years to 1.75 years. And then in tests, it gets a mean absolute error of 1.55 years. And when you estimate the infima of the 95% prediction interval, it gets an accuracy of 100% in minors. And lastly, regarding the distribution of the errors, as we said before, the method is very bad for younger individuals, but it is very good for older individuals with errors that are around the year of age. So it is competitive with the method that used to tease. And once again, as with the other methods, we obtain this explainability, these activation maps that show where the model is looking at to estimate the legal age. So this is a real example from the test set that is estimated as 18 and is in fact 18 years old. And you can see that the model looks at the clavicular epiphysis and at its function. So the conclusions of all these developments are the following. The methods for estimating legal age using AI can improve the accuracy of human experts, as I showed in the validation study. That when used as a decision support system, they can reduce the inter-expert variance, the maximum errors, and they can allow human experts to make more informed decisions. That a proper pre-processing is essential to avoid bias, improve generalization, and improve results. And that is why I focused on this in every method. And now David is going to talk about what we are working on right now, which is the multifactorial method and the multimodal approach.
So to wrap this presentation, I will just give a quick overview of the multimodal and multifactorial image-based age estimation project. One of the projects we have ongoing in Panacea, and as Venema was telling, the key objective of this project is to take age estimation a step forward, and our goal is to develop methods and models that fuse the information from different sources, but also using different modalities, such as DNA methylation, facial images, medical images, and as well as your traditional bone and teeth measurements and scoring. You have a somehow complicated schematic of what we aim to accomplish. So essentially, we pick up all the pre-trained models, and the idea is to develop learn aggregation models that can in all sorts of shapes, but in essence, here machine learning will be critical. To give you just some quick examples of the things we aim to accomplish, we aim, this is integrated also with other larger projects we have within Panacea. But for instance, in legal age estimation, we aim not only to integrate the X-rays, the OPGs, and the clavicle CTs together, but also embedded data from methylation of the DNA and facial photographs. Also, here, more related to the initial topic of age at death estimation, one of our goals is to develop one of the first methods to use the image of bones themselves. Our research will not be confined to the image. We also plan to use, for instance, 3D scans, but an image is something you can get, is a readily available equipment. Everyone has a camera, and here you kind of see of a conceptual prototype of what we aim to accomplish. So we can have imagine, just like Venema said, we can use, for instance, a convolutional neural network to automatically extract features from each of these skeletal features you are seeing, produce an integrated age estimate with, of course, with uncertainty, but also use the interpretability and explainability techniques from the realm of computer visions to try to look at what is the model focus. But also something we have in mind is also, for instance, to predict the annotations. If we have the annotations for this image, human annotations, we can predict our human would annotate, score a given feature, with advantage that we can have like a probabilistic scoring for a given feature, and we can fuse in this way a computer vision approach with a more traditional machine learning approach and a human expert-based approach. And we hope that this, in the end, will translate in something that is more reproducible and accurate, but also clearly explainable and understandable by a human expert that, in the end, needs to use this information to produce a forensic report. And that's it. I hope you've enjoyed. Here just some credits on the funding we have so far for these two major projects, and I would conclude on my side.